Good morning, everyone. This is Spin Dynamics, term 2. What we'll be doing in this term is study the algebraic foundations of spin dynamics and magnetic resonance, and looking one by one through the various structures and objects that we are encountering in our simulations, but from the mathematical point of view. So what we'll be doing is looking at spaces, metric spaces, algebras, groups, and things like that, and developing their theory in such a way as to fit it as a nice, firm, reliable foundation into this spin dynamics course. Chemistry departments and even physics departments oftentimes don't do a very good job of giving these things to people, and so we felt it was necessary to put in a very rigorous grounding in the mathematical aspects of spin dynamics, specifically into this course, and go through things in quite some detail, because it is really helpful at the level where you start designing your own spin dynamics simulation algorithms and power sequences and things like that. So as we'll see, it will provide us with a beautiful, firm foundation on which to build the rest of spin dynamics. So what I'll do now is, by way of introduction, I'll draw you a schematic of how the various algebraic entities we'll be encountering are related to one another. And throughout the next 10 lectures, we'll be slowly climbing up this diagram to try and build up knowledge as to how these things occur and how they are interrelated in the context of our simulations. So the fundamental thing that we'll be looking at is a set. A set is just a collection of objects. So set. And objects can be anything. They could be spins, they could be matrices, they could be vectors, and so on. So let's say wave functions. Some operators, some maybe super operators, and things like that. But the only thing we can do to objects in a set is group them together. Various subgroups, subsets, and so on. Multiplication is not defined, addition is not defined, not much is defined, actually. And although mathematicians, they like to study these sets for purposes of their own, for us, a set alone is not a very useful object. So what we'll do to sets when we study, for example, discrete symmetry groups, is we'll introduce a notion of multiplication, or superposition as it's also called, and then a set becomes a finite group. Finite group. For example, if the elements of the original sets were rotations, then the elements of the group would also be rotations, with the concatenation operation, sequential application operation, also defined. So we'll get into finite groups. On the other hand, if we'd like to do addition on this set, not the multiplication, what we'll require is, firstly, also a field of numbers. So field. A field, again, is of interest to mathematicians, but of little interest to us. So let's just say that field is where the numbers are coming from. So this would be either R, or it would be C, the field of real complex numbers in our case. And then what we'd like to define on this set is two operations. One is addition, so we can add the elements together. For example, we can add the two wave functions together. And the second is multiplication by scalars, so that we can actually take linear combinations of wave functions. We can take a couple of wave functions, multiply them by their respective coefficients, and get a linear combination. So from the set, we would like to have the addition operation, and from the field, we would like to have an operation of multiplication by a scalar. So an object which is a set with an addition and a multiplication by a scalar defined on it is known as a space. And it's populated by linear combinations of the elements from the set. It could be a linear combination of operators, it could be a linear combination of functions, and things like that. So let's say alpha psi plus beta phi. So objects of this type live on a space. What is missing from a space, at least as it is defined by the mathematicians, however, is the notion of distance and angle. Typically, because we only have the plus and the times a number, we do not have any notion of distance or angle. And so we would like to equate this space with a metric, or equivalently a scalar product. So if we take a space and we define a scalar product on it, we'll just use the Dirac notation, which is familiar to you. The result is known as Hilbert space. And this is where the wave functions well and truly live, because we now have the functions, we have their linear combinations, and we also have the scalar products, and therefore a notion of distance and norm, so a metric is defined as that space. So Hilbert space will be featured a lot, because this is where the wave functions typically operate. Okay, but let's take a look at this space. Again, we have defined an addition, multiplication, and the norm, but the multiplication is only by a scalar. We have not defined a multiplication by another member of the set. Or rather we did, but we went into a finite group which doesn't have the multiplication by a scalar or the norm. So what we'd like to have is addition, multiplication by a scalar, possibly a norm, but also the product of the two elements, because we would like, for example, to multiply two matrices together. So if we add a multiplication to this, the result in mathematics is called an algebra. And this is where we've got things like phi psi, like A operator, B operator, and things like that. We can optionally define a metric, but it's not strictly speaking necessary. So a set on which addition, multiplication by a scalar, and a multiplication between elements is defined is known in mathematics as an algebra. Alternatively, what we could define is not a product, but simply or just a commutator. So an operation, let's say a commutator AB, as you remember, is AB minus BA. And it needn't be identical to a product. You see, to define a commutator, you do not actually, strictly speaking, need to define a product. Only a commutator. You could, for example, define the commutation relationships for the Pauli matrix without resorting to any products. So a set on which this commutator is defined is known as a Lie algebra. Obviously, we could also define a multiplication, in which case the Lie algebra also becomes an algebra. Or we can take an algebra and simply extend it to have a commutation on it as well, in which case it becomes a Lie algebra. So there is a close correspondence between algebras and Lie algebras in this sense. But strictly speaking, a Lie algebra doesn't actually have to have a straight product on its bracket. A Lie algebra is something we'll be encountering a lot, because Lie algebra is where the spin operators live. And algebra is where the Hamiltonians live, because really to build a Hamiltonian you need other operations than the Lie bracket as well. You need extract products. Well, you remember what we can do to operators. We can exponentiate them. We can take a Hamiltonian and compute its exponential. So if we compute such an exponential, the result is known as a Lie group. A pretty complicated object. I will not go into the details right now. This is lecture 6 and lecture 7, I think. So we start sort of roundabout here today. But I will simply mention this, and I will not define what I say, that there exists a backwards map, the so-called tangent map, that returns you from a Lie group into the algebra. So, well, this is our grand picture. So we'll start here today. We'll take a look at the space today and tomorrow. We'll introduce finite groups in lecture 3. We'll go to algebras in lecture 4, then to Lie algebras, then to Lie groups, and finally put it all together into a nice, beautiful picture. So to relate this to magnetic resonance, Lie group is where the exponential propagators live. Lie algebra is where the spin operators live. Algebra is where the spin operator products and Hamiltonians live. Space is of wave functions, matrices, or anything that can be added together. Hilbert space includes the notion of distance, and finite groups usually refer to rotations, inversions, and various such finite symmetries. So that's the grand picture, and you have this grand picture in your handout. So do consult it. lest you get confused as to how these things are related to one another. And as I hope you've come to appreciate, this is a very beautiful general structure which underpins magnetic resonance in particular and spin dynamics in general. Okay, well, let's get started on this and introduce first the notion of a set and a space. Let's first take a look at our basic equations. Schrödinger equation, for example. So we remember that d psi by dt was minus I h psi. Let's say we found a solution to it. Let us say that psi1 is a solution and psi2 is a solution. If we take a sum of them, it is easy to see that a sum of these two would also be a solution, because this multiplication is linear, and so it threads through. So if psi1 is a solution to the equation and psi2 is, then their sum is as well. The same applies to Liouville von Neumann's equation. If we take d rho by dt is minus I h commutator rho, and you can start looking there and see that commutator relating algebra and the V algebra, so we'll get to that in a few lectures. But also, if we have rho 1, which is a solution to this equation, and rho 2, which is a solution, then their sum is a solution. Furthermore, if psi1 is a solution, then alpha psi1 is also a solution, and alpha rho 1, where alpha is any scalar, real, or complex. So you can see if we have a pair of solutions, then any of their linear combinations is also a solution. So, in other words, the set of all solutions to the Schrödinger equation is closed under addition and is closed under the multiplication by the scalar, and therefore the set of all solutions to Schrödinger's equation and Liouville von Neumann's equation is a space. Now, this is how space is defined in mathematics. I will now go through pretty rigorous definitions of what it actually is, because it is crucially important that we actually build a solid foundation, that you don't take anything I say on trust, because with things like that, there can be no such thing as a trust. You must know where it comes from and what the properties are. These are the very foundations of physics and perhaps of creation as well, depending on the philosophical outlook. So, generally speaking, a set D over a scalar field F, so field, is called a space if and we've got our three big criteria. Firstly, addition is defined. In strict mathematical notation, for any element, this sign means for any in mathematics, element A and element B belonging to a space V, their sum must also belong to V. That is to say, the set must be closed with respect to addition. Second thing is multiplication by a scalar is defined. So for any element A belonging to V, and for any element alpha belonging to the field F, it could be either real or complex numbers in quantum mechanics, alpha A must also belong to V. That is to say, the set is closed under multiplication by a scalar. And three, we will now demand a long list of properties for this addition and multiplication, because they have to be linear, associative, distributive, and things like that with respect to each other. So there's a long list given in your handout. So, for example, for any A and B belonging to V, A plus B must be equal to B plus A. So the addition operation must be commutative for it to be a space. Then for any A, B, C belonging to V, the result should not depend on how we put the brackets. A plus B plus C must be equal to A plus B plus C, the so-called associative law for addition. There must be a unique zero element, so there must exist, and that is the sign for existence, and that is a sign for the existence of something unique. There must be a unique zero element belonging to V such that for any element A belonging to V, A times 0 equals 0. So there must be such a zero element inside that space. There must also for each element be a unique opposite. So for each element A belonging to V, there must exist a unique element called minus A, such that minus A plus A equals the zero element. So we demand the existence of a unique opposite with respect to addition. You can probably see that the spaces you are used to, like function space in magnetic resonance or quantum mechanics, these things are fulfilled automatically. We're so used to them, we never even think about them, but they come into the fundamental definition of a space. What we also require is that the same laws of associativity and distributivity apply with respect to the multiplication by a scalar. That is to say, for any elements alpha and beta from our field F, and for any element A belonging to the space, we must have alpha beta A equal to alpha beta times A. So distributivity, associativity with respect to the multiplication by a scalar. We must also have the distributivity with respect to that multiplication, so for any alpha belonging to F, and for any element A and B belonging to V, we must have alpha A plus B equal to alpha A plus alpha B. So simple things like that. We must have distributivity also with respect to the multiplication on the scalar side. So for any alpha and beta in F, and for any A in V, alpha plus beta A must be alpha A plus beta A. And finally, we must have, well, that's the properties that the field has, but let's just note that it should be the case. There should exist a unique unit element in F, such that 1A equals A for any A belonging to the space. Quite a list, isn't it? But this is how a space is defined, and if any of these properties is not fulfilled, then it is not in fact a space. But you can easily check, or perhaps it is obvious, even without checking, that a set of wave functions, for example, is a space. A set of matrices of a given dimension is a space because we can add them together. There is a unique negative matrix, unique zero matrix, and things like that. So, in fact, surprisingly many objects that we will encounter in the context of magnetic resonance are in fact spaces. So, let's say a set of Hermitian operators is a space. A set of anti-Hermitian operators is also a space. And things like that. Right. So, what we now have is we've defined an operation of addition and multiplication by scalar. And so we have therefore defined a notion of a linear combination. And let's now proceed to define it. Let's define a linear combination, defines the notion of linear dependence, and ultimately the notion of a basis. Note that we don't yet have the notion of an orthogonal basis set or orthonormal basis set, because those require the existence of a scalar product, and the scalar product has not yet been defined. When it gets defined, our space becomes a Hilbert space, as that diagram shows. It takes a bit of time to get used to all this mathematical notation, but it's good for your soul, as it were. It breeds a certain kind of rigorous thinking that you'll find is quite beneficial in general for a scientist. Right. So, an element, let's call it V, belonging to a space V, is called a linear combination of elements A1 all the way, let's say, to AK, if there exists in the field of scalars such a set of scalars as would have the following property. The B is alpha 1 A1 plus alpha 2 A2 plus so on alpha K A K. So alphas live in our field and A's live in our space. And so if any element in V can be written out in this form, this is known as linear combination. One particular property that linear combinations have is related to what's known as linear dependence between the elements. So if we write things like that, alpha 1 A1 plus alpha 2 A2 plus so on alpha K A K, and let's say it equals to 0, and let us look at the implications. So the definition goes that a set of A's, so A1 all the way to AK, is linearly independent if the only way to produce a 0 is to set all coefficients to 0. This should be alphas, of course, not the case. So if there is no way to make a 0 except by setting all the coefficients to 0, then the set is called linearly independent. So if linear combinations are only 0 with 0 coefficients. If there are such non-zero coefficients as would make this 0, then the set is known as linearly dependent, and in that case one of the elements or more can be expressed as a linear combination of all the rest, and in that case the set is called linearly dependent. Now let us think about whether we can actually express every element of the space as a linear combination of some set of elements. So a set A1 to AN is called a basis set if its linear combinations span the whole of the space. So if every element of V can be expressed as a linear combination of the elements A1, A, N. It is important to know that this linear combination would only be unique if all the elements of this set are linearly independent. So we should add here, and it's a very important addition, a linearly independent set. It's very important in practice because when we start expanding wave functions, for example, in a given basis set, it is very important physically that such expansion be unique. And therefore, we can only properly rely on linearly independent sets as our basis sets. Although technically speaking, of course, we can generate the whole of V using a linearly dependent set, but the coefficients in such expansions would not be unique. And the coefficients are known as expansion coefficients. Right, so we have now defined a linear combination, linear dependence, linear independence, and we have defined a basis. The next thing is to recognize that because the original set had subsets, we could group the elements together, the resulting space would have subspaces. That is, if we take a subset of that set, which is closed under addition and multiplication of a scalar, then it will itself be a space. So, if V is a space, field F, and L is a subset, that's the subset of V that is closed under plus and the multiplication by a scalar, then L is a subspace. So a smaller set, this is also a space. Simple examples are, for example, if we take a three-dimensional space and we cut a plane through it, so let's say we put a plane, then for two vectors in a plane, if we stretch a vector in a plane, it stays in a plane. If we add the two vectors in a plane, the result is also in a plane. So any plane cutting three-dimensional space is a two-dimensional subspace of that space because it's a smaller set that is also closed under addition and multiplication by a scalar. Well, once we have those spaces and their subspaces, we can start adding them together, multiplying them together, and doing things to them. And so the next definition is of sum, direct sum, product, and direct product of subspaces. Again, notions of direct sum and direct product are something that, as active researchers, you have encountered already. You have all done spin dynamics simulations. But what we're doing here is putting them into, well, a reasonably rigorous context. I guess it's rigorous insofar as the standards of physics go, but mathematicians can probably poke holes in what I say for some special cases like infinite dimensional spaces and things like that. But for our purposes, this is perhaps as accurate as a discourse on these things would get. So, okay, let us now define a sum of subspaces. So a sum L1 plus L2 plus so on Ln of subspaces of, for example, subspace V is a set of all elements of the following form. Of the form L1 plus L2 plus L3 plus so on Ln, where each of these elements belong to its corresponding subspace. So if we take a set of all such sums, then the result is called a sum of the subspaces. If additionally these subspaces do not have any elements in common, so they are properly disjoint, and the only elements they have in common, because they must, is a zero element, then a sum is known as a direct sum. So if Lk only intersect at 0, then the sum is called direct. And the corresponding sign is this, and you have, of course, encountered this with block diagonal matrices, for example. They are built as direct sums of their individual blocks. And, well, a simple example would be if we take a plane and another plane. They do have a one-dimensional subspace in common, and so their sum, if we take the sum of these two planes, will be just a 3D space, so R3. But it is not a direct sum because they overlap on a line. If, however, we take a plane and a line that's perpendicular to it, then they only overlap at 0, and so this is a direct sum, which is also equal to R3. We should similarly now define the notion of a product of spaces, although we will encounter a difficulty here. You see, when we are working with a space, we do not in fact yet have the multiplication operation. So we should be careful, and it is possible to define a product of subspaces without in fact demanding for there to exist the product of two individual elements. So I will now define two things. One is called the Cartesian product of spaces. So Cartesian product. So if we take, let's say, L3 equals L1 cross L2, just the cross without the circles, it is a set of pairs of elements L1, L2, such that L1 lives in L1 and L2 lives in L2. So you see a cross product of spaces is a set of pairs, and this is in fact a set, not a space, because we have not defined how to add such pairs together. It's very easy to define, though. We can say, okay, we add pairs by, adding the elements, adding the corresponding elements, and multiplying them, and so on. In which case, the product becomes known as direct product. So, a space is a space spanned by the elements of the Cartesian product. Of L1 cross L2. So you've got a strict definition in the handout. So V1 cross product V2 is a set of all linear combinations. So the sum I over ij, a ij, where a is a scalar that comes out of the field F. These pairs, so they are called phi and psi, phi I, psi j in your handout, where phi's come out of L1 and psi's come out of L2, such that phi 1 leaves in this case V1, and phi 2 leaves in V2. Here else is the same as these, the handout jump notations, so if you get corrected. Interestingly, this cross product has the same linearity and associativity properties as we have imposed on ordinary products. It is quite convenient in practice because we can then start working with sets of spaces and subspaces and adding them and multiplying them together. And again, as you already know, in the context of spin dynamics, this becomes useful because the Hilbert space of a system of spins is a direct product of the spaces of individual spins and things like that. Right, so in particular, the direct product is distributive with respect to additions. So if we have phi 1 plus phi 2 cross psi, then it's phi 1 cross psi plus phi 2 cross psi. So these phi's live in one space, psi lives in a different space, but when we take a direct product of those spaces, this is how the sums get distributed. Same distribution law on the right-hand side of this. I will not rewrite this. And there is also the associativity with respect to the multiplication by a scalar. So C phi y C is a scalar cross psi is the same as phi cross C psi, which is the same as C phi cross psi. And C lives in our field of scalars. Right, so this is how we define the sum, the product, the direct sum, and the direct product of spaces from a very rigorous mathematical perspective. Right, so okay, once we've defined a space, what we can also define on this is various transformations. As we know, the operators we're dealing with, they're acting on this space in spin dynamics, and they're moving elements around or transforming them or in general doing something to them in a linear fashion. So we will now build something called linear operators on a space, and for that we need a notion of a map. Right, so if V and W are spaces, and they are always the same field over F, the procedure that takes every element of V and associates with it an element of W is called a map. And it is denoted like that: M taking V and mapping it into W. Now, we would like this map to be not just any map, because they can be very complicated. We would like it to be a linear map. So what we must have is M acting on alpha A, where A belongs to V, be the same as alpha M of A. So we should be able to take alpha out of the bracket under a map. What we should also have is that the map of A plus B, where A and B live in the space V, be the same as M A plus M B. So we have imposed the same linearity condition on the map as we have on quite a few objects before. So the spaces we are building are very essentially linear spaces. And the operations we are looking at over those spaces will have to be linear operations, well, at least for now. So that is the definition of a linear map. And if this holds, then M is called a linear operator, or alternatively the fancy word is holomorphism, and this MA is called an image of A in the space W. So we have taken a space V, an element A in it, and we have found it an image in the space W, and that is M under that map. Right. There is a special kind of maps which map spaces faithfully between themselves. It's easy to imagine an inaccurate map. For example, if we take every element of V and map them all into 0 in W, it's not a very useful map. I mean, it's linear, both of these relations hold, but it's not the kind of map which we find very useful because it dumps every element of V into just one element here, and it certainly wouldn't be reversible. We are particularly interested in the kind of maps which are faithful. That is, they do not lose any information and can actually be inverted. Because these are the sort of maps which we'll see a lot when we evolve the system in time. The evolution of the quantum mechanical equations is often reversible. And so the map that takes the system from the current time into some future point in time has to be a map which is in this sense faithful. It takes the state space of the system at a given time and maps it into the state space of the system in future. And it has to be a linear map in quantum. So these faithful maps we'll now be dealing with. So there's a theorem. I will not give any proofs here. You can look them up in mathematics literature. Unfortunately, we are so constrained on time that I will only give proofs and derivations for things which essentially belong to spin dynamics rather than textbook algebra. But if we have V and W that are spaces over, again, the same field F, and if A1 all the way to AN is a basis of V, and then B1, Bn is a basis of W, and they have the same number of elements, so these spaces have the same dimension, then there exists a unique operator that maps the basis A into the basis B. So the operator M that takes AK and brings it into BK, it can mix them, but so long as it maps them one into one and doesn't repeat itself anywhere, then such a map is unique. In a special case where M maps V into itself, so we have a map like that, V into V, M is known as automorphism because it takes the space and maps it into itself. And in a very special case when a map is between spaces of equal dimension and it is unique in such a way, the transformation, the map is known as isomorphism. And the isomorphisms will play central role when we treat quantum mechanical evolution, because the Lie group of propagators is in fact a group of isomorphisms. So we'll encounter these things later. Isomorphous spaces have the same dimension, so I will not prove it. It's a pretty general statement. But what it means in practice is something quite beautiful. It means that all spaces, let's say over the complex field C, if we have a space of anything of dimension n, it's isomorphous to Cn. And if it's over R, then it's isomorphous to Rn. The standard vector spaces that we are used to just columns of vectors. And it is incredibly useful in practice because these spaces can have pretty exotic objects living in them, like superoperators and things like that. But these theorems tell us that so long as a space has a given dimension and it's a space over a field of scalars C or R, then it has to be isomorphous through perhaps some very complicated map, but still isomorphous to good old vector spaces, which we know how to work with. And in particular, what this allows us to do is to replace perhaps very complicated spaces of some differential operators and things like that with matrix and vector spaces. And the great advantage of matrix and vector spaces is that computers can process matrices and vectors incredibly fast. Whereas they will normally have a certain amount of difficulty doing analytical transformations and integration and things like that. So it is essential that we should be able to map any kind of n-dimensional space into Cn or Rn, and these isomorphism theorems are actually telling us that this is always possible, and it makes quantum mechanics essentially, in the end, reducible to matrix algebra, which is quite useful in practice. Right, so what we'll now do is introduce a notion that arises from this map, from any space into Cn or Rn, the notion of a representation. So if we take a couple of elements in these spaces, map them into Cn, then linear operators will have to map into matrices because we know that it is matrices that transform vector spaces, and the corresponding matrix is known as a representation of an operator in Cn. So let us define it in a slightly more rigorous way than the chemists would define it in the chemistry mathematics course. So if we have a space V and the basis A, which is a set of A1 to An, we have a space W with a basis B, B1, Bk, dimension may actually be different, and let's say we have a map from V into W, then a matrix representation of M is such a matrix as transforms, so M, it's a matrix now, X equals Y, where X is an element of V written as a column of coefficients in the basis A, and this is an element of W written in basis B. So when we write X in basis A, it becomes a column of numbers, just the coefficients in the linear combination. When we write Y in its own basis B, it becomes a column of numbers. And we know that the most general possible linear map between columns of numbers is a matrix. And so this matrix is known as a matrix representation of this map from V into W, which is assumed to be linear operation. Well, we have a notion of representation, but we do not yet have any way of actually computing the coefficients of these matrices. And the reason is simple. As you remember, calculation of the coefficients involved scalar products. And so we now take the final step for this lecture. We shall introduce the notion of a distance on a space. That is to say, we will introduce the inner product and a norm to make it into a Hilbert space. Hilbert spaces are absolutely central in physics. Quite a few things have the property of a Hilbert space. Operators, there are operator scalar products, as we'll find in the next lecture. Obviously wave functions, obviously vectors. Anywhere, any kind of object with the notion of a distance is very likely to turn out to be a Hilbert space on closer examination. The field needn't be complex numbers, it could be real numbers, in which case the definition is simplified a little bit. But yes, Hilbert spaces are very well behaved, very nice to work with. It's always a very good thing when something you're working with turns out to be something as nice as a Hilbert space. There are pretty monstrous objects in spin dynamics, unfortunately. Things like matrix product states and density matrix normalization groups theory. They aren't even a space. Very difficult to work with. Right, so Hilbert space. So we'll take our space, and we now know quite a lot about it. And what we'll do is we'll introduce a map. But it won't be a map between spaces. It will be a map from a space into the field of scalars. So we'll introduce an operation, and I'll just use Dirac bracket notation for the scalar product. It will map pairs of elements, so it will map a direct product of a space and itself into a field of complex scalars. And you can see how the direct product came out, because we know that an inner product requires a pair of elements, and pairs of elements and their linear combinations live in the direct product of the two spaces. But, well, for now it's just a map, and it could well be a horrible map. And in order to call it an inner product, it must observe certain very specific properties. And the 5 properties are listed in the handout. Firstly, for any, in this case psi, I've switched a little bit closer to quantum mechanics notation because it starts looking very much like quantum mechanics. For any psi living in a space, psi scalar product must be greater or equal to 0. Secondly, for any phi and psi living in a space V, phi scalar product of psi must be equal to psi scalar product phi complex conjugate. Thirdly, for any phi, psi, and chi living in V, and for any alpha and beta living inside the field of complex numbers, I will specifically look at complex numbers now, not just any arbitrary field. We must have alpha, phi plus beta psi, scalar product chi. It must be linear and distributive with respect to the addition and multiplication by a scalar. So this has to be alpha phi chi plus beta psi chi. So you should be able to take scalars out of a bracket and spread the bracket through the plus operation. 4. If such a product is 0, it must necessarily imply that the element is 0. And finally, the so-called triangle relation, pretty fundamental for Hilbert spaces. For any phi and psi living inside our space, root phi phi plus root psi psi must be greater or equal than the root of phi plus psi phi plus psi. If you consider them as vectors and plot it on a piece of paper, you'll quickly see what a triangle relation actually refers to. This is to say that the hypotenuse of the triangle cannot be greater than the sum of its sides. Right, so these are pretty fundamental conditions, and interestingly, they are satisfied by a very large number of algebraic operations. Not just the scalar product that we're used to in quantum mechanics. We can create pretty exotic looking scalar products which would satisfy these properties, yet have nothing to do with physics. And now is the time where we need to restrict our scope a little bit and get a little bit less general, but perhaps closer to quantum mechanics in order to continue considering our specific cases. You, of course, remember that in quantum mechanics, for two functions, phi and psi, the scalar product was defined in the continuous case as integral from minus infinity to infinity, phi complex conjugate of x, psi of x dx. And if the functions were multidimensional, they depended on multiple arguments, it would be a multidimensional integral over the entire area on which these functions are defined. And in the case where we had discrete representations, phi psi would be a sum of the corresponding elements of those vectors, either infinite or finite number of them, phi n complex conjugate psi n. And by the end of the lecture, we'll actually define the relationship between these two forms. Now, in some cases, we would have functions that depend on both continuous and discrete variables, in which case the recipe is all continuous variables must be integrated over, and all discrete variables must be summed over, so we can actually have a mixed form scalar product. I'll leave it to you as an exercise to actually prove that all 5 properties are fulfilled with definitions there. It's not very difficult, but this is the so-called L2 scalar product that we encounter in quantum mechanics and its various applications like spin dynamics. Now, the product of an element with itself is known colloquially as the square of the norm. So we can also define a norm, phi, as a square root of phi scalar product with itself. Interestingly, the definition of a norm is in a certain sense equivalent to the definition of a scalar product, because a norm through so-called polarization relations induces a scalar product, and scalar product induces the norm, so you can define either one or the other, and the other one follows. So we just stick phi and phi in both cases here, and we get the definitions of a norm. But now that we have a scalar product and the norm, we can look a bit closer on the basis sets that we have picked up for our spaces. In particular, what we can now define is a notion of an orthonormal basis set. And an orthonormal basis set is such a basis in which all scalar products between elements are 0, and the scalar product between an element and itself, the norm, is equal to 1. So orthogonalized scalar products between different elements are 0, and normalized, the norm of the element is equal to 1. As we'll see later, such basis sets are particularly convenient to work with because many things that naturally occur in various expansions in that case turn to either 0 or 1, and it's therefore a bit more convenient to work with. So we can then take our psi and we can write the expansion in any basis set, so it will be a sum over k, psi k, coefficients, and the elements of the basis set phi k. So if phi is the basis of our space and psi are coefficients, then any function living in that space admits this kind of expansion. Well, let's take another function, let's call it chi, and have an expansion for that one. It will be a sum over k, phi k, phi k, so it will have an expansion in this basis phi with its own coefficients. But let us now connect this scalar product and this scalar product by computing it directly. So psi chi, if they are functions, we have to use the integral, so it will be an integral from minus infinity to infinity, psi complex conjugate of x, phi of x dx. Then I substitute this and this, and let's see what we have. We have then a sum over k, two different indices, the coefficients, psi conjugate k, m, chi k, then an integral from minus infinity to infinity, phi m star of x, phi k of x dx. Well, because we have imposed the orthonormality condition, this is delta m k. So what we then have is a sum over mk, psi m star chi k, delta mk, and delta is only non-zero when m equals to k, so we have a sum eventually over k, psi k star chi k, and that is in fact equal to the definition here. So you see, if we take a space of continuous functions and have a scalar product like that, but then define a basis on that space and expand everything in that basis, then the scalar product in the space of the resulting coefficients becomes the discrete scalar product as defined in a Hilbert space of vectors, whereas the original Hilbert space was a Hilbert space of functions. So this defines a connection between discrete and continuous representations. The spaces involved are frequently infinite dimensional, so we have to demand that the functions be square integrable for these things to actually converge. But this is one of the specifics of quantum mechanics, of course. Things have to be square integrable, otherwise the infinities creep into probabilities, and the problem becomes physical. So it's in a way a natural requirement that things be square integrable in quantum mechanics. Okay, so what we've done today is we introduced the notion of a space. We have defined linear combinations, multiplications by a scalar. We've defined linear combinations, then basis sets as things that linear combinations are of. Then we introduced the notion of a representation, where the basis is fixed and we only store the coefficients in that basis set. As soon as we wanted to know those coefficients, we wanted a scalar product, and so we introduced the scalar product, shifted a little bit closer to quantum mechanics, and then showed that there are discrete representations and there are continuous representations, and demonstrated the connection between the two in the terms of the scalar products that we have defined. Okay, this was for functions, and we'll do identical things. Well, they will be identical conceptually, but rather different in the actual implementation. We will, in the next lecture, define a space of operators